Hello and welcome to Science Night Tales. I am glad you have found this quiet moment to look up. Tonight we are going to change the way we see the stars. We often think of them as permanent fixtures, burning steadily forever. But that is only because our lives are so short. We are going to speed up time just enough to see the truth that every star is on a long, slow journey. From the cold dust clouds where they are born, through billions of years of shining, to their quiet, beautiful endings. You do not need to memorize astrophysics tonight. You are safe to observe from a distance. You can simply let the rhythm of their lives wash over you. If this perspective helps you find calm in the vastness of time, you are welcome to like or subscribe. For now, let go of the clock and let's watch the stars unfold together. When we look up at the night sky, most of us see the same thing every time. Small points of light, fixed, silent, unchanging. Night after night, year after year, the stars seem to hold their places. They rise, they set, they return, and over a human lifetime, they appear almost perfectly still. It's easy to believe that this is all there is, that stars are permanent fixtures, background lights, something closer to scenery than to process. And in a way, that belief makes sense. Human time is short. We measure change in seconds, minutes, years. Even a century feels long. Against that scale, the sky looks frozen. Nothing up there seems to hurry. Nothing appears to grow or age or fade. But that sense of stillness is not a property of the stars themselves. It's a property of us, our eyes, our clocks, our limited span of attention. Because beyond what we can notice, beyond what we can feel, every star in the sky is moving through a long and orderly sequence of change. Not dramatic, not rushed, just slow. Extremely slow. So slow that an entire human civilization can rise and fall without leaving the slightest mark on a single stellar moment. A star that looks the same tonight as it did thousands of years ago is not standing still. It is simply changing on a timescale that ignores us completely. Right now, as you listen, stars are forming. Others are settling into long periods of stability. Some are quietly exhausting the fuel that has sustained them for billions of years. And others have already completed their transformations, leaving behind remnants that still occupy the sky, even if we don't recognize them as such. All of this is happening at once, and not as a story with a beginning and an end, but as a continuous cycle repeating across the galaxy. The night sky is not a snapshot, it is a cross-section, a single frozen frame taken from a process so vast that motion disappears when we try to observe it all at once. When we say a star is born, we are not describing a moment. We are describing a span of time so long that the word birth barely applies. When we say a star dies, we are not describing an ending in the human sense. We are describing a transition that unfolds across millions of years, sometimes longer. Nothing sudden, nothing urgent, just change. Stretched thin across deep time. This is why stars feel eternal. Not because they last forever, but because their lives unfold at a pace that does not intersect with ours. A single breath you take lasts a few seconds. A star's earliest formation phase can last tens of millions of years. A single night of sleep might feel long. A star's stable phase can last billions of years. So when you look up and see a familiar pattern of lights, what you are really seeing is a mixture of ages. Some of those points began forming before Earth existed. Some will continue shining long after the sun has changed beyond recognition. Some are already in later stages of transformation, even though they look calm and steady from here. Distance adds another layer to this quiet confusion. Light takes time to travel. So the stars you see are not the stars as they are now. They are the stars as they were, minutes ago, years ago, thousands of years ago. In some cases, millions of years ago. The night sky is not only a collection of distant objects. It is a record, a layered archive of different moments in stellar history, all arriving at your eyes at the same time. This means that the sky above you tonight contains stars at every stage of their existence. You just can't tell which is which by looking. Their light is too steady, their changes too gradual, their rhythms too slow. And that slowness is the key. Because the story of stellar life is not one of chaos or urgency. It is not a sequence of explosions strung together. It is mostly quiet, mostly stable, mostly patient. Stars spent the majority of their existence doing very little that looks dramatic from the outside. They form slowly, they settle, they remain steady for spans of time that dwarf planetary histories. Change comes, but it comes gently, even when the physics involved is extreme, even when the energies are vast. But the pace remains calm, predictable, orderly. This is not a universe of constant upheaval. It is a universe of long processes, and stars are among its most consistent examples. So, as we begin this journey through stellar life cycles, there is no rush, no countdown, no need to brace for impact. We are not moving through time at human speed. We are adjusting our perspective, letting our sense of now stretch outward, letting our idea of change slow down. We will move step by step, from the earliest stages, when stars are not yet visible at all, through long eras of stability, and eventually toward transformation and aftermath, but always at the same steady pace, always without urgency, always with the understanding that what feels like stillness is simply motion spread thin across time. The night sky has been telling this story since long before humans learned to look up. It will continue telling it long after we are gone. Not loudly, not dramatically, just steadily. And the first chapter of that story does not begin with light. It begins in places where stars have not yet formed at all. Regions where matter is spread out, where change is slow, where the earliest stages of stellar existence take shape so gradually that nothing seems to be happening, until eventually something does. And that is where we go next. Not suddenly, not quickly, just slowly moving into the calm beginnings of stellar formation. Out here, before anything shines, there is space filled very lightly, not empty, but close. Large regions where gas and dust are spread thin across enormous distances. These regions are called nebulae. They don't have clear edges. They don't have a center you can point to. They are not compact clouds drifting through space. They are vast volumes measured in light years, where particles are separated by distances far greater than anything we experience on Earth. Inside a nebula, atoms move slowly, very slowly. Temperatures are low, motion is gentle, nothing is rushing toward anything else. From a human perspective, nothing seems to be happening at all. And yet, this is where stars begin. Not with a flash, not with an ignition, but with accumulation. Gravity is already present here. Not strong, not dramatic, just persistent. Every particle of gas has mass. Every grain of dust contributes a tiny pull. Over time, spans so long they are difficult to imagine, those tiny pulls begin to matter. Not in days, not in years, but over hundreds of thousands, millions of years. Material that happens to drift slightly closer together feels a slightly stronger pull. That pull gathers a little more matter, which increases the pull again. The process feeds itself. Quietly. Nothing collapses all at once. There is no moment where a nebula suddenly becomes a star. Instead, there are regions within the nebula where density becomes just a little higher than the surroundings. Pockets where matter is no longer evenly spread. These regions are still cold, still dark, still invisible to the naked eye. But they are no longer perfectly balanced. Gravity begins to guide material inward, slowly, patiently. As gas drifts inward, the region grows denser. As density increases, gravity strengthens. As gravity strengthens, inward motion becomes slightly more organized, still gentle, still without urgency. This is not motion you could watch unfold. If you were somehow present, nothing would appear to change. 1,000,000 years could pass, and the scene would look almost the same. Yet throughout that time, matter would be inching closer. Distances shrinking, energy rearranging. All of this happens long before there is light, long before there is heat, long before anything could be called a star. What we often call stellar birth is really a long preparation, a gradual shift from spread out matter toward concentration, from quiet balance toward slow inward movement. Temperature begins to rise, but only slightly. Pressure increases, but remains low by everyday standards. There is no threshold crossed in an instant, only conditions that slowly evolve. As material continues to gather, the central region becomes warmer, not hot, just warmer than before. Heat here is not a signal of violence. It is simply the result of motion becoming more organized. As particles fall inward, gravitational energy converts into thermal energy. This heating is gentle, spread across enormous volumes of time. Nothing flares, nothing ignites. There is no brightening yet. What exists now is called a protostar. But even that word can feel misleading, because a protostar is not a small star waiting to turn on. It is a region of gas still very much in the process of becoming something else. Fusion has not begun. Light has not emerged. The object remains wrapped in the material that formed it, surrounded by dust, hidden from view. If you were looking with ordinary eyes, you would see nothing at all. This stage can last for millions of years, longer than the entire history of human civilization. During that time, the region continues to collect matter, slowly growing more massive, slowly warming, slowly increasing pressure at its core. Everything about this process resists hurry. The laws governing it do not allow shortcuts. Gravity works at the pace mass permits. Energy accumulates only as fast as motion allows. There is no option for speed, and that slowness is not a flaw. It is the natural rhythm of star formation. In many nebulae, this process never completes. Regions gather some material, then disperse again. Gravity is not always strong enough. Nearby forces can interrupt. Gas can drift away. Not every accumulation leads to a star. Only when conditions remain stable for long enough does the process continue, and when it does, it continues patiently. Over time, the central region becomes dense enough that pressure rises significantly. Temperatures climb further, still not enough for fusion, but enough to mark a transition. The object is no longer just a gathering of particles. It has internal structure, an inward gradient, a sense of center, yet it remains calm. No sudden changes, no dramatic thresholds crossed. This is important to understand because it reshapes how we think about stars. They are not born, they are assembled. They are the result of long preparation rather than sudden creation. What we call the beginning is simply the point where accumulation becomes irreversible. And even then, the process unfolds slowly. As this protostar continues to contract, time continues to stretch. Millions of years pass. Pressure builds. Temperature rises steadily. The conditions needed for sustained nuclear fusion approach, but do not arrive all at once. The system adjusts gradually. Matter settles. Energy redistributes. Everything moves toward balance, and eventually, without a clear moment to point to, fusion begins. Not as an explosion, not as a flash, but as a steady reaction that quietly starts and continues. That next phase does not feel like an ending to this one. It feels like a continuation, a smooth transition from gathering into stability. And that calm transition is where we go next. From slow accumulation into the long, steady phase where a star begins to shine and remains for a very long time. As accumulation continues, where the region does not suddenly become something new, it simply grows warmer, denser, more compact. What we call a protostar is still not a clearly defined object. It is not a surface, not a boundary, not a sphere you could outline. It is a volume where conditions are slowly changing. Gravity continues to guide material inward, not faster, just more consistently. Gas falls toward the center, releasing energy as heat. Pressure rises, temperature follows. All of this happens together over long spans of time. Inside this warming region, particles move more quickly than before. Collisions become more frequent. Energy spreads outward through the surrounding material. Nothing is balanced yet. The inward pull of gravity is still stronger than the outward pressure created by heat. So contraction continues, very slowly. The core temperature climbs from thousands of degrees to hundreds of thousands, then higher still. Even at this stage, fusion has not begun. The conditions are close, but not complete. Hydrogen nuclei are present in great numbers. They move faster now. Collisions occur more often, but the forces that keep nuclei apart still dominate. Electromagnetic repulsion remains stronger than the thermal energy pushing particles together. So the system waits, not consciously, not intentionally, simply following physical law. As mass continues to accumulate, pressure increases further. The core becomes hotter, denser, more constrained. Energy has fewer directions to escape. Eventually, temperatures reach millions of degrees. At this point, something subtle changes, not visibly, not suddenly, but statistically. Collisions between hydrogen nuclei begin to reach energies high enough that, once in a while, two nuclei come close enough to interact. Most collisions still fail. Particles bounce away, repulsion wins. But occasionally, fusion occurs. One reaction, then another. At first, these reactions are rare. They do not dominate the system. They do not yet provide enough energy to counter gravity. But they matter. Each fusion reaction releases a small amount of energy. That energy adds to the pressure inside the core. The balance begins to shift. This is not a moment. There is no instant where a protostar becomes a star. Fusion does not turn on like a switch. It ramps up, gradually. As more fusion reactions occur, energy output increases. Outward pressure strengthens. Eventually, a point is reached where inward gravity and outward pressure match. Not perfectly, but closely enough. Contraction slows, then stops. The system settles into equilibrium. This balance is what defines a star. Not brightness, not visibility, but stability. A star is a region where gravity pulling inward is balanced by energy pushing outward from sustained nuclear fusion. This balance is quiet, orderly, long-lasting. Once established, it can persist for billions of years, but reaching it requires patience. Even after fusion begins, the surrounding material continues to adjust. Outer layers rearrange, energy flow stabilizes, the system fine-tunes itself. Throughout this time, there is still no drama, no explosion, no sudden expansion. Light gradually becomes able to escape more freely as surrounding material thins. The star becomes visible, but visibility is not the defining feature. Equilibrium is. At this stage, the star has entered its longest phase, the phase where change slows further, where processes repeat, where conditions remain steady across spans of time that dwarf human history. But before that stability fully settles, the protostar passes through a long transition. Fusion increases slowly, pressure rises to meet gravity. Internal temperatures stabilize. Each adjustment happens in response to the last. No step is skipped, no shortcut is possible. The system finds balance because the laws governing it allow only balance or collapse, and collapse no longer dominates. What's important here is not the threshold itself, but how gently it is crossed. We often imagine fusion as something violent, as something explosive. But inside a forming star, fusion is simply the next stable outcome. A quiet response to conditions that have been slowly prepared. Millions of years of accumulation lead to millions more years of steady reaction. Nothing about this process is rushed. Nothing needs to be. The star does not hurry into existence. It arrives when conditions allow, and not before. As equilibrium settles in, the star becomes a reliable source of energy. Hydrogen fuses into helium. Energy flows outward. Light travels through the star's layers and into space. From a distance, the star appears constant, unchanging, but that appearance rests on an enormous amount of internal order, a continuous balancing act that repeats moment by moment. Now, with fusion established and equilibrium in place, the star enters a long stretch of time. A period defined not by formation, but by endurance. A phase where change continues, but slowly, predictably, over billions of years. For most of a star's existence, nothing dramatic happens. There is no visible struggle, No sudden change in direction. No moment that would feel like a turning point. After the slow gathering of a nebula, after the long warming of a protostar, the star enters a state that will define nearly everything that follows. This is the main sequence. It is not an event. It is not a peak. It is simply balance. At the center of the star, hydrogen nuclei move with quiet persistence. Temperatures are high, but not growing rapidly. Pressure is immense, but held in check. Gravity continues its inward pull, trying to compress the star further. At the same time, energy from nuclear fusion presses outward. Neither force wins. They hold each other evenly. This balance is not fragile. It is self-regulating. If the star begins to contract slightly, pressure and temperature rise. Fusion speeds up, just enough to push back. If the star expands a little, fusion slows and gravity gently tightens its hold. No intervention is required. No adjustment is conscious. The system corrects itself automatically. This is what stability looks like in the universe. Hydrogen fusion at this stage is unremarkable in its rhythm. Protons merge slowly. Energy is released in small, consistent amounts. Photons begin a long journey outward, sometimes taking thousands of years to reach the surface. Nothing rushes. From the outside, the star appears calm. Its brightness remains steady. Its size changes very little. Its light arrives with dependable regularity. Stars like the Sun have existed in this phase for billions of years. Many will remain here for billions more. This is not a temporary condition. It is the default. When we look up at the night sky, nearly every visible point of light is a star in this state, quietly fusing hydrogen, quietly holding shape, quietly existing. The main sequence is not the middle of a story. It is the story. Time stretches here. A star does not experience days or seasons. It does not register years passing. Millions of years drift by without altering its basic structure. Hundreds of millions more follow, almost indistinguishable from the last. Change still occurs, but at a pace too slow to feel. Hydrogen is being converted into helium, one nucleus at a time. The total supply decreases, but imperceptibly. At any given moment, the star remains almost exactly what it was before. Even this transformation is orderly. Fusion does not consume fuel unevenly. It proceeds at a rate determined by the star's mass, nothing more. Smaller stars burn slowly. They sip their hydrogen, conserving it across unimaginable spans of time. Some will remain on the main sequence longer than the current age of the universe. Larger stars burn faster. Their higher pressures increase fusion rates. Their lives are shorter, but still measured in millions of years, not moments. No matter the size, the pattern holds. Balance first, stability sustained, change deferred. This phase does not demand attention. It does not announce itself. It simply continues. From a human perspective, it might seem uneventful, but from a cosmic one, it is everything. Planets form during this time. Orbits settle. Radiation becomes predictable. If life is to arise, it does so under this steady light. The main sequence provides consistency. It offers patience. A star does not hurry toward what comes next. It does not anticipate exhaustion. It remains where it is as long as equilibrium allows. And equilibrium allows a great deal. Even as helium slowly accumulates at the core, nothing changes on the surface. The star's appearance remains familiar. Its output remains reliable. There is no warning that fuel is being used, no signal that balance will one day fail. The universe does not rush its transitions. Instead, it lingers. This long period of stability teaches a quiet lesson. That motion does not require disturbance, and change does not require urgency. Most of existence unfolds like this: steady, regulated, almost invisible in its progression. Only much later, after vast amounts of time have passed, after hydrogen has thinned beyond replacement, will this balance begin to shift. But not yet. For now, the star remains where it is, held between forces, sustained by gentle reactions, defined not by transformation, but by persistence. This is the longest chapter of a star's life, the calm center of its timeline, a state that lasts so long it can feel permanent. Even in its most stable state, a star is not frozen in time. Nothing appears different from the outside. Its light remains steady. Its size holds. Its rhythm continues without interruption. And yet, change is already underway. Deep within the core, where temperatures are highest and pressure is greatest, the balance of materials is slowly shifting. Hydrogen, once abundant, is being transformed into helium, not quickly, not unevenly, but continuously. Each fusion reaction leaves behind a small trace of change. One nucleus becomes another. Energy escapes. The core's composition adjusts by an amount too small to notice in any single moment. There is no boundary where stability ends and change begins. They overlap. For a long time, hydrogen still dominates the core. Fusion proceeds as it always has. The outward pressure remains sufficient to counter gravity. The star remains in equilibrium. But the mixture is no longer exactly the same as it was. Helium does not behave like hydrogen. It occupies space differently. It does not fuse as easily at the same temperatures. As it accumulates, the core grows denser, almost imperceptibly. This increase in density causes a subtle response. Gravity presses inward just a little more. Temperature rises slightly. Fusion continues, adjusted, not disrupted. From the surface, nothing reveals this shift. Brightness does not flicker. The star does not swell or dim. Its spectrum remains familiar. Stability absorbs the change. This is how most cosmic processes unfold, not as reversals, but as quiet rebalancing. Over millions of years, the hydrogen-burning region of the core slowly contracts. Fusion becomes more concentrated. The surrounding layers respond gently, adapting without visible disturbance. No alarms sound, no phase ends. The star does not grow weaker. It does not age in a human sense. It simply continues with a slightly altered interior. Even this interior change follows a measured pace. A star spends far more time adjusting to small internal differences than it ever will in visible transformation later on. For much of its life, these changes remain hidden. They matter only because they accumulate. This is not a story of decline. Nothing is being lost prematurely. Energy output remains steady. Balance remains intact. The star is still doing exactly what it was formed to do. If anything, this gradual change highlights how resilient stability can be. The system adapts without disruption. Forces respond smoothly, not abruptly. Gravity increases its inward pull as the core grows denser. Fusion responds with slightly higher rates. Pressure adjusts. Again, no winner, only compensation. From far away, across interstellar distances, the star appears timeless. Observers separated by millions of years would see almost the same object. Its light carries no obvious record of the slow transformation at its center. Time continues to pass. Unannounced. Eventually, hydrogen in the core becomes scarce enough that fusion can no longer proceed there as before. But this moment lies far in the future. For now, the star remains within the long corridor of equilibrium. What changes first is not appearance, but condition. The internal balance becomes more delicate. The margin for adjustment narrows slowly. Yet even then, nothing sudden occurs. Fusion migrates outward, beginning in shells around the core. The center itself becomes inert helium, hot, dense, and silent. Still, the surface remains calm. The star does not react emotionally to this shift. There is no sense of urgency. Processes unfold according to pressure and temperature alone. This quiet progression reminds us that transformation does not require drama. It does not arrive with signals or warnings. It develops beneath continuity, not against it. Most of a star's evolution happens this way, hidden within normalcy, unseen by distant observers. The universe favors patience. By the time visible changes begin, the internal groundwork has already been laid over immense spans of time. The star does not suddenly become something new. It reveals what it has been slowly becoming all along. For now, though, equilibrium still holds. Light still streams outward. Balance remains the dominant theme. Change is present, but it is quiet, embedded, and entirely compatible with stability. As the conditions at the center continue to shift, the balance that once held so effortlessly begins to reorganize. Not collapse, not failure, adjustment. The core, now richer in helium, no longer produces energy through the same steady hydrogen fusion that defined so much of the star's life. Fusion has not stopped entirely. It has moved. Around the inert center, a shell forms where hydrogen still fuses. This shell becomes the new primary source of energy, and it produces more energy than before, not suddenly, gradually. With this additional energy, the outward pressure in the star increases. Gravity responds, as it always does. The layers above the core begin to shift. The outer regions expand. This expansion is not explosive. It does not tear the star apart. It unfolds slowly over millions of years as the star seeks a new balance between inward pull and outward pressure. As the surface moves outward, it cools slightly. The light changes character. Colors drift toward the red end of the spectrum. This is what defines the red giant phase. Not violence, not instability, just scale changing to match new internal conditions. The star becomes larger, but less dense overall. Its surface gravity weakens. Its outer layers drift farther from the core, held more gently than before. Inside, the core continues to contract under gravity's steady influence. As it contracts, it heats up. Temperature rises without any external signal. Again, nothing is rushed. The red giant phase is often described as dramatic only because the difference is visible. Compared to its earlier state, the star now occupies more space. But the process itself remains orderly. Energy flows outward. Layers respond. balance is re-established temporarily. For stars similar in mass to the Sun, this expansion marks a long luminous period. They shine brightly not because they are unstable, but because their internal structure has shifted into a new configuration. Hydrogen continues to fuse in shells. Helium waits in the core, growing hotter and denser. The star is not nearing an end. It is moving into another sustained state. Time stretches here. This phase lasts long enough for surrounding systems to adapt. Planets, if present, experience gradual changes rather than sudden disruption. The star's outer layers become more diffuse. Material drifts more freely. Yet gravity still holds the structure together. Nothing breaks apart. For more massive stars, the same principles apply. Internal evolution leads to expansion. Shells of fusion stack around the core. Each layer responds to the changing pressure beneath it. The scale increases. The rhythm remains controlled. This expansion is the natural response to altered energy distribution. No direction is chosen. Physics simply follows conditions. At no point does the star decide to change. There is no threshold crossed with force, only a gradual rebalancing, continuing what began deep within long ago. The star's appearance now reflects its interior more openly. What was once hidden becomes visible, not abruptly, but clearly. And still, this is not an ending. The red giant phase is a bridge. It connects long stability with what comes next. It allows the star to redistribute energy, mass, and structure in preparation for future states. The core continues to evolve. Temperature rises, pressure increases. Eventually, new forms of fusion will become possible for some stars. For others, different outcomes await. But none of that happens yet. For now, the star exists in expansion without urgency. Larger, cooler at the surface, brighter overall. A new equilibrium holding just as steadily as the one before, only shaped differently. This phase does not interrupt the star's life. It continues it. Internal evolution flows outward, shaping form without chaos. And as the star settles into this expanded state, it quietly prepares for paths that will soon begin to diverge. As the star remains expanded, another factor becomes impossible to ignore: mass. Not as a measure of importance, not as a ranking, simply as a condition that has been present since formation. The amount of material gathered at the beginning quietly shapes everything that follows. Stars with lower mass and stars with higher mass obey the same physical rules: gravity, pressure, energy balance. What differs is how long each stage lasts and how many stages are possible. In lower mass stars, gravity compresses the core to a limited degree. Temperatures rise, but only so far. Fusion progresses slowly and conservatively. Hydrogen fusion dominates for most of the star's existence. When hydrogen becomes scarce in the core, helium accumulates. Eventually, helium fusion becomes possible. This transition does not happen suddenly. The core continues contracting. Temperature increases steadily, patiently, until conditions allow helium nuclei to combine. For stars with modest mass, this marks the highest level of fusion they will achieve. The energy produced is enough to maintain structure, but not enough to initiate further stages. Heavier elements require higher temperatures, and temperature is controlled by gravity. In more massive stars, Gravity compresses the core far more intensely. Pressure and heat rise to levels unreachable in smaller stars. Fusion continues beyond helium. Carbon, oxygen, neon. Each stage unfolds as fuel becomes available and conditions permit. These stages are not accelerated by urgency. They follow the same balance principles seen earlier: energy outward, gravity inward, structure responding over time. What changes is duration. Higher mass leads to faster fuel consumption. Energy production increases, time shortens. A massive star may pass through fusion stages in millions of years that smaller stars would never reach in billions. This is not efficiency, it is consequence. Lower mass stars persist quietly, maintaining fewer fusion processes over immense spans of time. Higher mass stars experience more internal transitions, but for shorter periods. Neither path is preferred. Neither is exceptional. Each is the natural outcome of initial conditions. Mass determines how many equilibrium states are available. It determines how far fusion can proceed. It determines which elements are formed and which remain unreachable. As fusion advances in heavier stars, layers develop. Shells of different fusion reactions surround the core. Each shell exists only while fuel remains. When a fuel source diminishes, energy output shifts. The structure responds. The star adjusts again. In lower mass stars, these transitions are fewer. In higher mass stars, they are more numerous. But the governing logic remains unchanged. There is no branching chosen at random. There is no turning point emphasized as dramatic. The future is shaped gradually from the beginning by mass alone. This does not mean the end is approaching quickly. It means the range of possible endings is already defined. Some stars will shed outer layers gently. Some will compress into dense remnants. Some will release energy in brief, intense phases before settling into compact states. Each outcome is the result of accumulated conditions rather than sudden change. Even now, during expansion, the star is already aligned with its eventual state. The pace differs, the path length differs, the destination differs. But the process remains continuous. Mass does not push the star forward. It simply sets the boundaries within which physics operates. Nothing is wasted. Nothing is added later. The material gathered in a diffuse cloud long ago still governs what is possible now. As time continues, the star will move naturally towards states allowed by its mass. No step will interrupt the flow. No stage will arrive unannounced. The next phases are not surprises. They are extensions. What lies ahead depends neither on chance nor intention, only on quantity and time. And with this quiet clarity, the full range of stellar life cycles begins to come into view, not as endings, but as completions shaped from the start. As stars with lower mass continue through their extended lives, the changes ahead arrive without urgency. Fuel in the core becomes increasingly limited. Hydrogen has long been consumed there. Helium fusion, if it occurs, proceeds steadily and then slows. Energy output adjusts. Gravity responds. The balance that once held the star in its earlier form begins to shift. The outer layers are no longer held as tightly as before. This does not happen all at once. There is no sudden release. Over long periods of time, the star's outer material drifts outward. Gas moves away gradually. dust follows. The surrounding space filled slowly with material that was once part of the star's structure. From a distance, this process appears calm and extended. The star is not ending abruptly. It is redistributing matter back into its environment. These expanding layers form what astronomers call a planetary nebula. The name is historical, not descriptive. There is no planet involved and no explosive behavior implied. The nebula spreads outward at measured speeds. Over tens of thousands of years, it thins. Eventually, it blends into the surrounding interstellar medium. What remains at the center is not absence, it is a remnant. The core of the star persists as a compact object known as a white dwarf. This remnant is dense. Its mass is comparable to that of the original star. Its size is far smaller. Fusion has ceased. There is no longer enough pressure or temperature to support nuclear reactions. Yet the white dwarf is not unstable. It does not collapse further. It does not expand again. It exists in a state supported by the principles of quantum mechanics, where further compression is resisted without the need for energy production. The white dwarf retains heat accumulated during earlier stages. It releases this heat slowly. Over billions of years, it cools. There is no sudden transition from warmth to cold. Temperature decreases gradually, following predictable physical laws. As time passes, the white dwarf becomes dimmer. Radiation output declines. The object remains present, even as visibility fades. This cooling process extends far beyond human timescales. White dwarfs can persist longer than the current age of the universe. Their evolution continues quietly, without interruption. There is no defined moment that marks an ending. There is no final state reached quickly. Matter that once participated in fusion now exists in two forms. Dispersed material contributes to future clouds of gas and dust. The compact remnant holds its structure indefinitely. Neither outcome suggests disappearance. The nebular material does not vanish. It mixes into surrounding regions. It becomes available for future accumulation. The white dwarf does not resolve into something else. It remains cooling slowly, occupying space with stability. This pathway is the most common stellar outcome in the galaxy. Stars with mass similar to or lower than the Sun follow it naturally. There is nothing unusual about this result. It reflects the limits imposed by mass and energy balance. The star has completed all the fusion stages available to it. No further reactions are possible. No additional transitions are required. What remains is continuity. The environment receives material. The remnant maintains form. Time continues without disruption. In this way, low-mass stellar life cycles conclude not with disappearance, but with redistribution and persistence. The process emphasizes endurance rather than finality. Change occurs, but structure remains. As one complete life cycle settles into this stable configuration, attention naturally shifts outward. Other stars began with more mass. Their internal conditions allow additional stages. Their outcomes follow different paths, governed by the same rules, but extended further. And so, from these quiet endings, the perspective widens towards stars whose lifetimes unfold under stronger gravitational pressure and different limits. When stellar mass increases, the sequence of internal processes extends, but the pace remains measured. The early stages follow familiar rules. Gravity draws material inward. pressure rises, temperature increases, hydrogen fusion begins, just as it does in lower mass stars. Energy flows outward. A stable balance forms between gravity and radiation. For a long time, nothing appears different from the outside. Inside, however, conditions continue to change. Greater mass means stronger gravity. Stronger gravity means higher pressure in the core. Higher pressure allows additional fusion stages to occur once hydrogen becomes limited. Helium fusion begins gradually. It does not arrive as a sudden transition. It emerges as temperature and density cross specific thresholds. Helium nuclei combine to form heavier elements. Energy production continues. The star remains supported. As each fuel becomes scarce in the core, contraction resumes. Temperature rises again. A new balance is established. This sequence repeats. Carbon fusion becomes possible in stars with sufficient mass. Later, neon fusion, then oxygen, then silicon. Each stage occurs in a progressively smaller region near the center. Each stage lasts less time than the one before it. Yet even these shorter stages extend far beyond human lifetimes. Thousands of years, hundreds of years, sometimes less. Despite these changes, the star does not behave erratically. It does not flicker between states. It follows a clear, ordered progression determined by physics. Internal structure becomes layered. At the center, the heaviest fusion reactions occur. Surrounding layers continue earlier stages simultaneously. Hydrogen may still fuse in an outer shell, while heavier elements form deeper within. And these layers remain separated by temperature and density gradients. They are not mixed randomly. They persist in relative stability. Energy flows outward through all layers. The surface responds gradually. Brightness and size adjust over long intervals. From the outside, these stars may appear steady. Their internal complexity is not immediately visible. The increase in complexity does not introduce urgency. It does not imply acceleration toward an endpoint. It reflects the availability of additional fusion pathways. Each fusion stage releases less energy than the previous one. The balance becomes harder to maintain. Gravity's influence grows more dominant. Still, equilibrium holds until physical limits are approached. Iron eventually forms at the core in the most massive stars. This element does not release energy when fused. At this point, fusion no longer supports the star. This outcome is not abrupt. Iron accumulates gradually. The core composition shifts over time. Throughout this process, the star remains governed by the same forces. There is no new principle introduced. Only the consequences of mass and energy balance continue to unfold. The increasing number of fusion stages does not add drama. It adds structure. Complexity grows because conditions allow it. When conditions no longer allow it, the process changes direction. This pathway illustrates how mass expands possibility without altering the underlying rules. Lower mass stars follow shorter sequences. Higher mass stars follow longer ones. Neither path is exceptional. They represent different expressions of the same physical framework. As the internal layers continue to adjust, a boundary approaches, a limit defined not by time, but by stability. Beyond this point, balance can no longer be maintained in the same way, and as that limit draws closer, the star's structure prepares for its final transformation. Without haste, without signal, and without escalation, the internal layers approach their limits.
To
Fusion has carried the process as far as it can. Energy production no longer offsets gravity. Pressure at the core is no longer renewed. What follows is not an act of destruction. It is a physical adjustment. The core contracts. Not suddenly, but decisively. Gravity acts without opposition. As the core compresses, outer layers respond. They begin to move inward as well. Momentum builds through the star's structure. This inward motion does not continue indefinitely. At extreme density, resistance appears. The core stiffens. A rebound occurs. Energy moves outward through the surrounding layers. Material that once fell inward is redirected. The star's outer regions separate from the core. This transition happens quickly by astronomical standards. Yet even here, the process follows clear physical limits. No additional force is introduced. What emerges is a redistribution of matter. Elements formed during earlier fusion stages are carried outward. They move into surrounding space. Over time, they disperse. This dispersal is not uniform. It unfolds across large regions. The material slows, mixes, and spreads. Heavier elements, carbon, oxygen, silicon, iron, are no longer confined. They become part of the surrounding environment. Their presence alters the composition of nearby regions. This process does not end immediately. The expelled material continues to expand for thousands of years. Shock interactions soften, energy dissipates. Eventually, motion settles. The event itself is brief. Its consequences persist. The surrounding space now contains additional matter. Future generations of stars will form from this material. Planets may later incorporate it. This outcome is not exceptional. It is one of several possible paths determined by mass. The physical sequence does not prioritize drama. It prioritizes balance. When balance cannot be maintained internally, it shifts externally. Matter moves to locations where stability is possible again. Throughout this process, the core remains. What happens next depends on its remaining mass. Density increases, structure simplifies, the energetic phase passes. What remains is compact, ordered, and quiet. The redistribution phase does not represent an ending. It represents a transition of material from one state to another, from concentrated to dispersed. The star's influence continues not through light, but through matter. The surrounding region now carries a record of internal processes that unfolded over millions of years. Those records remain long after visible traces fade. The adjustment completes without ceremony. Motion slows, temperatures decrease. What follows is not emptiness, but persistence in a different form. And at the center of this outcome, something dense and stable remains, ready to be understood on its own terms. The remaining core settles into a state defined almost entirely by density. Its mass has not disappeared, it has not dispersed, it has been compressed. Matter occupies far less volume than before. Atomic structure no longer sets the scale. Electrons and protons are no longer separate. Under sufficient pressure, they combine. The result is a dense arrangement dominated by neutrons. This configuration is not exotic by intent. It is the natural outcome of gravity acting without interruption. The size of this object is small compared to the star that preceded it. Its mass, however, remains comparable. A volume similar to a city contains more matter than entire planetary systems. Density becomes the defining property. Not heat, not brightness, density. This state is stable within specific limits. Gravity pulls inward, internal forces resist further collapse. Balance is restored, rotation becomes more noticeable. As the core contracts, rotational speed increases. Angular momentum is conserved. The process is gradual and predictable. The result is a steady rotation, sometimes measured in seconds, sometimes faster. This rotation does not introduce instability. It becomes part of the object's long-term behavior, a consistent pattern maintained over extended periods. Energy continues to leave the object, not as sustained fusion, not as explosive release. Radiation emerges slowly. Particles escape along defined paths. The output is limited and regular. There is no ongoing transformation here, no progression toward another state. The structure has reached a configuration that can persist. Time passes, thousands of years, millions, more. The object remains largely unchanged. Cooling occurs gradually. Rotation slows imperceptibly. Surrounding space adjusts to its presence. Gravitational influence extends outward. Nearby matter responds. This influence does not require activity. It exists as a consequence of mass. The object does not need to emit energy to matter. In some cases, additional material approaches. Interaction may occur. If so, it follows known physical rules. But even these interactions are limited. They do not redefine the object's nature. They add minor variation to a stable form. The core does not collapse further unless mass increases beyond a threshold. Below that limit, equilibrium holds. Structure remains intact. This outcome is not rare. It represents one of the standard endpoints for massive stars, a common resolution to earlier processes. The earlier stages involved change, accumulation, fusion, expansion, release. Here, change slows. The defining features are consistency and endurance. The object occupies a narrow range of possible states. Once there, it remains. This persistence does not imply stillness in an absolute sense. Internal motion continues. Particles maintain pressure, rotation continues, but the large-scale structure is fixed. No further stages are required. The energy once generated through fusion is no longer produced. What remains dissipates slowly. Thermal energy decreases. The object grows quieter over time, less detectable, less influential beyond gravity. Yet it continues to exist, not as a phase, as a condition. This form does not signal an ending. It represents a long-term arrangement of matter, one that can persist for spans far exceeding the active life of the original star. In this state, the life cycle pauses, not temporarily, indefinitely. Only mass can alter the outcome now. Without it, the structure remains unchanged. The processes that led here are complete. The matter has reached a configuration where forces balance again. What follows depends on the limits of mass, on how much remains, on how tightly it is bound. Beyond this point, outcomes diverge only when those limits are exceeded, and that threshold marks the final transition still ahead. Across the galaxy, this sequence does not occur once. It occurs many times, in many places, at many moments separated by long intervals. Material that once belonged to earlier stars remains present. Gas drifts, dust spreads, elements persist within diffuse regions. These regions are not isolated. They exist within larger patterns of motion. Orbits around the galactic center continue. Within these broad motions, matter slowly gathers again. Gravity acts without preference. Where density increases, accumulation resumes. There is no starting signal, no global timing. Different regions proceed independently. Some areas remain quiet for extended periods, others begin gradual contraction. The process does not synchronize. From dispersed material, new concentrations form. Temperature increases slowly, pressure follows. What develops resembles what has occurred before, not in exact arrangement, but in physical sequence. Fusion begins only when conditions allow it, not earlier, not abruptly. Once active, a new star enters its longest phase. Stability dominates. Change proceeds at a measured pace. This pattern is common. Most stars spend the majority of their existence in this balanced state. It defines the average condition of stellar matter. Over time, fuel diminishes. Internal composition shifts. Structure adjusts. Outcomes depend on mass. They always have. They always will. Lower mass stars disperse outer layers gradually. Their remnants cool and persist. Higher mass stars proceed through additional stages. Material released during later stages does not vanish. It spreads into surrounding regions. It mixes with existing gas. Elements formed deep within stars remain available. Carbon, oxygen, heavier nuclei. These elements do not carry memory. They do not mark origin. They exist as material. Over long intervals, they become part of new structures. Not immediately, not directly. Time passes between generations, millions of years, often longer. During these intervals, nothing appears to happen. From a human perspective, change is imperceptible. From a galactic perspective, the process continues uninterrupted. Star-forming regions appear and fade. Spiral arms shift position over hundreds of millions of years. Orbits evolve, yet the underlying sequence remains consistent. Accumulation, fusion, adjustment, dispersal. No single star defines the process. Each is one instance among many. Each follows the same physical rules. The galaxy does not require coordination. Local conditions determine outcomes. Physics applies uniformly. At any given moment, different stages coexist. Some stars are forming, others remain stable. Some are nearing structural limits. Remnants persist alongside active stars. White dwarfs cool. Neutron stars rotate steadily. Nothing here represents completion. Nothing signals a final state for the system as a whole. The cycle does not accelerate. It does not aim toward resolution. It continues at a pace set by mass and gravity. This continuity does not imply repetition in detail. Each region differs slightly. Each star has a unique configuration, but the overall process remains recognizable across distance, across time. The galaxy contains vast empty regions. It also contains dense concentrations of matter. Both are necessary for the pattern to persist. Without dispersal, material would remain locked. Without accumulation, new stars would not form. Balance emerges from both. The scale involved exceeds individual lifetimes. It exceeds recorded history. It extends beyond direct observation. Yet the sequence can be described, not because it is dramatic, but because it is consistent. Stars do not need to be observed to follow these paths. They proceed regardless, unchanged by attention. As older stars complete their processes, new ones begin elsewhere. The timing overlaps. The transitions remain gradual. There is no central moment, no defining event, only continuation. The galaxy remains populated by stars in many stages at once. Their distribution shifts slowly, their numbers change modestly. Over billions of years, the pattern persists. Material cycles through states. Energy is released, then diminishes. Nothing about this process demands interpretation. It operates according to known conditions. It unfolds without urgency. The perspective widens. Focus shifts away from individual outcomes. Attention rests on continuity. Across the galaxy, the same processes repeat, not identically, reliably, and as one star completes its sequence, elsewhere another has only begun. The processes continue, not quickly, not all at once. They proceed at the pace set by mass, distance, and time. Stars form where conditions allow it. They remain stable for long periods. They change slowly, often without visible signs. Nothing in this sequence requires urgency. There is no moment that demands attention, no stage that must be reached by a certain time. Across the galaxy, matter moves through these stages repeatedly. Gas gathers, fusion begins, energy flows outward. After long intervals, structure adjusts, material disperses, remnants persist. These transitions do not interrupt the system, they sustain it. Time stretches between each phase. Millions of years pass without noticeable change, sometimes billions. From a human perspective, this duration feels abstract. From a physical perspective, it is expected. Stars are not rare events. They are ongoing outcomes of ordinary conditions. Where density and gravity align, formation proceeds. Where fuel is present, stability follows. Where fuel diminishes, structure adapts. Nothing about this requires acceleration. Nothing seeks completion. Material released during later stages does not disappear. It spreads through surrounding regions. It becomes part of the environment. That environment remains available for future accumulation, not immediately, not deliberately. Long periods of stillness separate each generation. Regions remain diffuse. Temperatures remain low. Then, gradually, conditions shift. Density increases slightly. Motion becomes noticeable only over extended time. From these slow changes, new stars emerge. Not as replacements, not as successors, simply as outcomes. At any moment, many cycles overlap. Some stars are just beginning, others remain unchanged, others approach later stages. This overlap is constant. It does not peak, it does not resolve. The galaxy holds all stages simultaneously. Formation, stability, transformation, and persistence coexist. There is no central timeline, no shared starting point. Each region follows local conditions. Some areas remain inactive for extended periods, others cycle more frequently. The variation does not alter the overall pattern. The processes do not require observation. They proceed whether they are noticed or not. Light travels outward from stars formed long ago. It reaches distant regions long after its source has changed. What is seen is often delayed, yet the underlying processes remain current. They continue regardless of when light arrives. Nothing here concludes. Nothing begins absolutely. Material remains in circulation. Energy flows outward and dissipates. Balance adjusts. Over time, the composition of the galaxy changes slightly. Heavy elements become more common. Gas slowly redistributes. But these changes unfold gradually. They do not announce themselves. They accumulate quietly. The scale involved softens the idea of endings. Individual stars complete their sequences. The system does not. Cycles persist because conditions persist. Gravity remains. Matter remains. As long as these exist, the process continues, not endlessly in identical form, but without a defined stopping point. There is no requirement to follow the sequence forward, no need to anticipate what comes next. Everything unfolds on its own schedule. Attention can remain with the present description. Stable states, slow change. The absence of urgency is not emptiness, it is continuity. Stars are not static points, they are stages within a longer flow. That flow remains consistent. Each phase transitions into the next without instruction. No signal marks the shift, only conditions changing gradually. This repetition does not imply monotony, it reflects reliability. Across vast distances, the same physical rules apply. Across deep time, the same sequences occur. Nothing accelerates toward conclusion. Nothing pauses for significance. The processes remain indifferent to scale of attention. They are neither fast nor slow by preference. They proceed as allowed. As older stars release material, other regions remain quiet. Later, those regions may gather. This spacing in time allows continuity. It prevents depletion. It maintains balance. The galaxy does not exhaust itself quickly. It evolves over extended durations. Changes accumulate slowly. None of this demands focus. It does not require interpretation. It simply continues. For long intervals, the dominant state is stability. Stars remain unchanged. Energy output remains steady. This steadiness defines most of stellar existence. Transformation occupies a smaller fraction. Dispersal follows without urgency. Even remnants persist for long periods. White dwarfs cool gradually. Neutron stars remain stable. These objects do not signal endings. They represent phases within continuity. Over time, they contribute material back to the environment, sometimes directly, sometimes indirectly. Nothing is wasted. Nothing is hurried. The scale of time involved allows patience. Processes unfold fully. Outcomes stabilize. There is no final arrangement, only current conditions. As the cycle repeats, no stage demands emphasis. Each is necessary. Formation does not override stability. Transformation does not negate persistence. The system remains balanced through repetition, not through intervention, not through intention. This balance allows the galaxy to remain active across long spans. It does not rush towards silence. It does not accumulate chaos. Instead, it proceeds evenly. Change occurs, then it settles. The description can pause anywhere within this sequence. Nothing is lost by stopping. Nothing is gained by continuing faster. The processes remain available. They do not require completion. Across the galaxy, stars continue their slow paths. Some have just begun, others remain steady, others approach dispersal. None of these states is privileged. Each occupies its place within the whole. The sense of scale widens, attention loosens, specific outcomes matter less. What remains is continuity. Process without urgency, change without tension. And within that steady repetition, nothing needs to conclude.